very happy to speak to you about my research. And as you said, I'm going to talk, of course, also about the knowledge bases and these kind of things. And that's also the title of the talk is on language models and knowledge bases. So first, let me introduce myself. So in my life, I had three goals that I wanted to achieve. I wanted to be rich, and I wanted to have the freedom to work on what I want to work on, and I wanted to have a permanent position. Yeah. So these were the goals that I was hoping for. Maybe you can somehow relate to these goals. And I studied in my bachelor in Germany in cognitive science. That's everything that is basically AI before it was cool. Then I did my master in computer science also in Germany, and then I did my PhD also in Germany at the Max Planck Institute. And in terms of my three desiderata that I wanted to achieve during this time, I was exactly here. Yeah. So I had neither money nor freedom nor a permanent job. And then I went on to become a postdoc at Microsoft Research in the Silicon Valley. And there I worked on the Bing shopping engine. Have you ever heard about the Bing shopping engine? Anybody? Yes, Miwish did, but yeah, because you saw the talk before, yeah, but nobody else. And the reason is that this project actually died 2 years after I left Microsoft Research, and 4 years after I left Microsoft Research, the entire lab was shut down. Yeah, and I don't know whether it was because I was there or because I left. So this lab no longer exists. Yeah. So then, in terms of my desiderata, I had to work on the Bing shopping engine, so I was not free. It wasn't a permanent job, but boy, did they pay well. Yeah, so I was plainly in the money bubble. And then I became a postdoc at Université, actually quite close to here in Paris, where I'm currently based. And so this being the French public service, I had to move out of this left bubble, out of the money bubble. But I was free to do whatever I wanted, even though it was not a permanent job. It was a postdocship. Yeah, so I was here. And then I went back to Germany and I became a research group leader at the Max Planck Institute in Germany. And this was for the first time I could move into an intersection because Max Planck pays very well and they give us the freedom to work on what we want to work on. But so the message I'm passing is if it's so nice, yeah, then it's not forever. It's not a permanent position. Yeah. So I'm over here. Yeah. And then 1 year later, I became an associate professor here at Telecom Paris. This being the French public sector, I have to move out of the money bubble. But we are pretty free to do what we want here, and it's a permanent position. So I was here. And then 3 years later, I became a full professor, and also my institute is changing names all the time, and it's currently called Institut Polytechnique de Paris. And so this job change that finally allowed me to go here. Yeah. And this is where I currently am in this diagram. Now, it's very hard to make any talk today without somehow relating this to language models. So I will not forego this occasion. And so I asked ChatGPT about myself. So to introduce myself via ChatGPT, and I asked, how many papers did Fabian publish in database venues? And as you see, it's doing pretty well. So it found the papers it found like database venues, and also found like the papers I published there. So it does a join actually between these two queries, and it's pretty good. It found like all works. And then I'm not sure, right? But I computed several times, and it said, here's one paper, 1, 1, 2, 2, 1, 1. And then it says, in total, I found 8 publications. But I mean, I counted several times, and this is just not 8. Yeah. So this is very surprising that actually a task that's quite complex is like finding the database venues, joining it with the papers I wrote there, and then counting fails in the most trivial step, which is the counting. Like even my son can do the counting, although he would be unable to find the database journals. Yeah. So it's quite surprising actually. And so this leads into this topic of this talk, which is that language models are amazing and they're great for a great number of tasks, but they do have some trouble, most notably, as we just saw with aggregation, count, and joins. So whenever you want to count something or aggregate, then the models are not so good, although they always wrap their wrong answers in a deceptively convincing language. So here in this example, the model will, for example, say, if you like, I can list which 8 exactly papers, so you can check. So it's like super convinced of what it's saying, even though it's wrong. Yeah. And so we say like language models know how to talk even when they don't know what to say. Yeah, so this is the message. They can give different answers if asked in different ways or different languages. So my favorite example is this one. I asked, it was ChatGPT 3.5 at the time, yeah, so it's a bit older, but it's still funny. I asked, did Elvis Presley die? And the chatbot says yes. And then I ask, is Elvis Presley alive? And then it says, there is no definite answer to this question. Yeah. So you see, there's the same question, right? And give different answers. This is why there's now an entire field of science that's called prompt engineering. Yeah. So most papers nowadays are in one way or another about we engineer the prompt. And that is because the models are like so difficult to to harness and put on the right path if you don't have the right prompt. So there's a lot of criticism of this term because people say like engineering at least is a science that has proceeds according to systematic improvements and has a guaranteed outcome, whereas prompt engineering has none of this. But that is a nearly like philosophical discussion. Speaking of which, we there are more philosophical differences also between the language models and the way we perceive them. So language models are probabilistic by nature. So we started a project with Bosch, the German car manufacturer, and they were building a chatbot for their engineers. And so the question that the engineers wanted to ask is, should I connect the red cable or the blue cable? Yeah, and then the model would reply, probably the red cable. Yeah, with the probability of 85%. Yeah? So this is a fundamental problem that language models are probabilistic while truth is not. I mean, for the most part. Yeah. So there is a divergence between the way language models see reality and the way reality is, in particular because language models reply by what is most probable, like from a distribution point of view over the sentences, and not necessarily with what is like true. Yeah? So these are two different things. They're designed to generalize and not memorize. So if you give them the two blue dots here, the models will interpolate and extrapolate the blue line. So, so if they give them two poems of Shakespeare and say this is poems of Shakespeare, and say make a third one that is about, I don't know, language models, it will come up with a third one. And this is because it can extrapolate, and that's a very good property. But in some applications, you don't want the model to generalize. You want it actually to memorize. You want, here are the two dots. These are the Shakespeare poems, and it's just these two and nothing else. And this is very hard to do with models because they are designed to generalize and not to memorize. Yeah, they will invent and forget and extend and hallucinate at their own discretion, which is their force and their their weakness. Yeah. So going beyond these technical challenges, there are societal challenges that come with language models. So if you think this through, yeah, what if everybody now just uses language models like chatbots instead of web search? Yeah, I mean, you can still use Google, but Google, you just use Gemini, yeah? Gemini. So what would happen then? Yeah, and then it's a very interesting question that appear. Yeah? So what happens if they all use just say ChatGPT or Gemini or some other model and no longer visit the web pages? Yeah, and that has interesting consequences because it means that the pages are used by the chatbots, but they are no longer visited. And now you see that this can easily go very wrong if people, for example, no longer visit Wikipedia. Yeah, so they still get the content from Wikipedia, but they don't visit the pages, which means that Wikipedia gets less donations and less contributors and might potentially die. Yeah? Already now they're seeing their traffic like go down. And so this is actually a danger, and not just for Wikipedia, but also for the language models, because if Wikipedia dies, yeah, so then so will the language models, yeah, because they have nothing more to be trained on. Yeah, and so these are interesting questions that go beyond the pure technical part of language models, and that go into the like societal, legal, or philosophical perspective. So other questions are: do users have a right in the answers they receive? Yeah, you get an answer, for example, recipes, your cooking recipes. Can you sell these? Can you make a book out of them? And the answer is yes, you can. But you have no right in these. So if somebody else takes your book of recipes and sells it as well, then you cannot claim a copyright because the recipes were generated by machine. And so these are interesting questions, yeah, that actually pop up when you think this through. What if we all just use language models? And this goes beyond the pure technical questions that we typically address. Yeah. So we have a survey article on this with a lawyer actually together, where we elaborate on these things. So what can we do? Yeah, I mean, what people do, yeah, is that at least for certain types of data, they still use structured data. For example, my university here, Telecom Paris, has a list of employees, and the list of employees is not stored in a language model, so they didn't fine-tune a model for all the employees, but it's stored in a database, of course. Why? Yeah, because they can easily audit it. Yeah. Because they can update it. So if I ever get fired or like I get a salary rise, then they can just update it. They answer deterministically. So if they ask the same question several times, they're going to get the same answer, which is like a valuable advantage. Plus, they can answer factual queries at a fraction of the cost. So if they had trained a language model on all the employees of Telecom Paris, then they would want to like ask, does this person work there? Then they would need to run an inference, which is like very costly. It's a GPU and like loops of inference. Whereas if you just store it in a database, then it's like a nanosecond issue, like of a few cycles. Yeah. So there are some cases where we still use structured data, be it list of employees, be it list of products with their prices, like Amazon or something. Yeah, they don't store their products in a language model because the model would hallucinate. Yeah, would for example say, oh, we have these two types of screws. We probably have this screws as well. No, you don't. Yeah, but the model cannot like not generalize. Yeah? So these are like inherent limitations in language models that make them less suited for any application where you need structured and like Boolean data, the crisp data, that's yes or no. Yeah? And so for these types of data, it's still databases that are indispensable. Yeah? Now maybe we talk again in 5 years, you tell me, yeah, you see Fabian is all wrong. Yeah, no, language models do it all. But for now, they don't. And so then the question is, how can we marry these two types of systems? Yeah. So on the one hand side, you have the language, like how, like people want to interact with natural language, and on the other hand, you have the what, that is like the data, the crisp data that's actually stored, and you somehow want to bridge this gap. This is what this talk will be about. And they're like, we are not the only ones to work on this, right? Several people have tried to establish this, and some are pretty successful at this, like GraphRag and stuff all exists. Yeah. So we're gonna not like show this in our pipeline. Also, we don't have it working anyway. We're just gonna illuminate like some aspects of this pipeline that we have worked on, like stepping stones, like our small contributions on this big picture of marrying these two worlds. Yeah. And so by way of introduction, we're gonna like not talk about myself being employed at my university, which maybe not so many people care about. Like we're going to talk like more about like Elvis Presley, which maybe more people care about. At least I do, yeah. And we're not going to talk about databases. We're going to talk about knowledge bases, which is of course no novelty to you guys because this is a part of the of the entire project. And also last month's talk was also already on knowledge bases. So we talk about like graphs where the nodes are entities and the edges are relations between these entities. And we'll see how we can marry these two things. So the first issue that appears is actually how you can disambiguate. And that's something that is often swept under the rug. So when we read like, is Elvis alive? Then of course, yeah, we think Elvis Presley, yeah. But there are many Elvises, yeah. So which one is it? And so if anybody who wants to link like natural language text to structured knowledge, like a knowledge base, needs to solve this issue of ambiguity, like what do the words actually refer to? And so here I want to show like an approach that like 10 years ago would have been like hyper complex, like we use like convolutional neural networks and alignment features and embeddings and attention matrices. And nowadays, this type of architecture is trivial. Yeah. And so the reason I'm showing this here is to show that with something very simple, you can actually achieve state-of-the-art performance. So what we do is we embed the mention of the word. So in the sentence, is Elvis alive? We embed the word Elvis. And for every single entity in the knowledge base that shares some textual overlap with the entity mentioned, we also embed this entity. And then we just compute the similarity between the two. Yeah? So that's something that's like very simple, yeah, given today's complex things. And but that performs actually surprisingly well. So now you hear the numbers, and this is the only time I show numbers actually in this in this talk. And I show the numbers for two reasons. And the first one, why I'm showing the numbers, because our numbers actually here at the bottom, right? Our base model as a research, our model is actually worse than the best one. Yeah, it's actually the best one is 91, and we are 90. And I'm showing these numbers to sensibilize us for the fact that these are always numbers on samples, because these are like test samples, like test set. And the test sets naturally come with a confidence interval, because they are like typically a few hundred or a few thousand manually annotated samples. And if you add the confidence interval around this percentage, then you see that we are statistically indistinguishable from the top performing system. Yeah? And this is something that I think we should have in mind when we publish these numbers, that it's not about like I'm 0.1% better or like in 1% better. Yeah. But these differences often go away if we consider the confidence intervals. And so you see here, not just that we are statistically indistinguishable from the top one, but more worryingly, that also the top one, that is the one from 2020. Can you see my mouse actually? Can you just not underline? I can see you. Can you see my mouse actually? Yeah, okay. So you see the top one from 2020 is statistically indistinguishable from the one in 2015. Yeah. So they published this paper saying, look, we are 1% better, but this is actually not statistically significant. So in 5 years, actually no progress. And I think this was published in 2021, so there's still no progress. Yeah. So this is this message. Yeah. So that there is always a confidence interval to be taken into account around these things. Good. Now, so we have talked about the left part here, a bit about the language part, but since you guys are more on the knowledge domain, so we move rather quickly to the right hand side of this this diagram, and now we talk about the link between the two. On the left hand side we have a sentence, right hand side we have the knowledge base, and here I'm posing an issue with logical reasoning. For example, all true heroes are immortal. Is Elvis Presley alive? And from the knowledge base you know that he's a true hero. And is Elvis Presley alive? Then it follows that yes. So let's look into this. How can we like reason on this type of natural language queries, natural language text? Yeah. And here is what a language model does. Here I give the setting. All true heroes are immortal. Elvis is alive, or a true hero is Elvis alive. Answer and reasoning steps. And then the model will output reasoning steps. We'll say, let's think step by step. Yeah. Premise, Elvis is alive or true hero. Premise, Elvis is a true hero. Conclusion, Elvis is alive. And this is actually the correct answer. So if you think this through, this problem at the top, then the second one tells you either he's alive anyway, or a true hero, and then he's immortal, which means also he's alive. So the answer is correct. But can you see what is the issue actually with this reasoning steps at the bottom? If you look at this, first premise or something, second premise. Do you see this? I don't know whether you can see this issue. Yeah, I see people nodding. Yeah. So the second premise, actually, I mean, I agree, Elvis is a true hero. Yeah, but this actually never appeared in the text. Yeah, I mean, nobody's ever said Elvis is a true hero. Yeah. So this is a hallucinated premise, and this means that if this premise is hallucinated, this reasoning is actually invalid. Yeah? So the conclusion is correct, but the reasoning is invalid. And that is alike to the calculation that's in the top right in the slide. So if you divide 16 by 64, yeah, you can cross out the 6 and you arrive at 1/4. And the result is correct, but the way in which you arrive at this result is incorrect. Yeah, and of course you want to avoid this type of reasoning, because even if the answer is correct, if the model learns to reason this way, then it might reason wrongly on future instances. So you're interested not just in the correct answer, but also in the correct path to that answer. Yeah, this is the wrong way to arrive at a correct result, and you want to avoid this wrong result. So what can we do? Here's one way. We use a checker language model, and we say, can you please check this reasoning? And then the checker language model will tell us this reasoning is faulty. Yeah. Do you see the brilliance in this or the problem with this? I don't know. This is the typical thing that people in my domain do, yeah. But I mean, if you don't trust this language model on the left, yeah, then there is no reason to trust this language model on the right. Yeah. If you trust the checker language model, then use that language model directly for the reasoning. Yeah. And if you don't trust it, then there's no use in applying it. Yeah. So you can't check one untrustworthy thing with another untrustworthy thing. Yeah. It doesn't make any sense. So then let's try like a logical reasoner. Yeah. So here's a logical reasoner. All true heroes are immortal. Elf is a true hero. Elf is alive. Correct answer. Validated. Grounded. Everything's great. But the reasoner will still say it's, if you take like a symbolic reasoner, the reasoner will say it's like a faulty reasoning. Why is that? Because the logical reasoner cannot see that immortal means alive. Yeah? So the logical reasoner will say, yeah, you said they're immortal, but you ask alive is not the same thing. Your reasoning is faulty. Yeah? So we have the two issues. Like language models are like good at understanding language, but they actually they cannot be trusted because they're not transparent. And logical reasoners, like symbolic reasoners, can be trusted, but they are unable to deal with language. And so here we come with kind of a vehicle that will like kind of solve this issue for us. So we translate this reasoning step into like some pseudo logic, where you see that this is all true heroes are immortal becomes X is a true hero implies X is immortal, which is not beautiful. Yeah? It's some pseudo logic. Yeah. So we have a universal quantification and we have implication, and that's it. And otherwise, we just take the sentences as atoms. So you see that negation and implication gets like pulled out, but is alive and is a true hero. These are just like atomic statements that we cannot further analyze. So this is a syntactic exercise that works by you can think of it as a regular expression. So what do we do now? How to bridge this Elvis is immortal, Elvis is alive? We use textual entailment. And textual entailment, although it's supposed to be an error, sorry. Textual entailment says that Elvis is immortal entails that Elvis is alive. So this should be entailment character, sorry for this. And we ask an entailment model to judge all pairs of sentences. And in this way, we get, for example, that is immortal entails is alive. And this we translate to an implication. And then we can use a logical reasoner, like we use a Gensen style logical reasoner. And this reasoner will then like prove this conclusion. And so then the language model is still used for this textual entailment, but only for a very limited part of the overall equation, and the entire proof is done by the logical reasoner. So this is kind of a neurosymbolic approach. So it's called Vanessa, validating answers by natural language entailment and statistical sentence analysis. No, syntactic sentence analysis. Huh? So this is the art to come up with these acronyms. And so these are the results, basically, that the Vanessa can keep up often with the precision of language models, but in addition can give this transparency that language models cannot give us. So now we have talked only about the knowledge base, and we haven't talked about what the language model actually does, and what language models actually therefore is not like reasoning but telling us stories. Yeah, so they're very good at coming up with types of like textual content. Yeah, and but how do we know whether this textual content is actually good what they produce? Yeah, and we tend to evaluate what they produce by standard measures like bleu, rouge, and other French color names, sometimes by human evaluation. But is that the right thing to do? And we say it's not. Because we went to the literature in the humanities, that is the sciences that really do evaluate the quality of stories. Like, for example, they take the fables, or they take like student essays, or they take like fairy tales, and they evaluate to what or why these stories are popular. And their criteria for evaluating whether a story is good or bad is not at all a bleu score, but is relevance. Like, how relevant is the story that the student wrote with respect to what we asked them to write? How coherent is the story? How much empathy do you feel with the character's emotions? And how surprising is the end, and so on. And speaking of surprise, here is the surprise. These automated measures that we have, like bleu, rouge, and these, correlate very, very weakly with the measures that are actually used in the humanities. Which means that what we should actually use are the language, the measures from the humanities, and we like release a corpus of these stories that are annotated with the scores by humanities by humans, and then we evaluate the models on them and see. And actually, as you see, the models are not actually good. The standard scores are not good unless you use a language model as a judge, and then it's not so bad. So the LLMs are actually pretty good at judging their own stories. So this is the lesson there. Good. So wait, sorry, this is not something I want to show. Uh, this. Uh, yeah, here we go. Good. Now we've talked a lot about the left-hand part. Now I want to talk about the right-hand part as well, about this knowledge base. So where does this come from, actually? So knowledge bases can be built by information extraction from text. That is, we can actually give as input Elvis Presley is a famous singer. We can use a language model, and then we can produce the output, the knowledge base on the right-hand side. It's actually one way in which this can be done, and we wrote a book about this, how this can actually work. There's an array of techniques. What we did is we started with an extraction from Wikipedia first. And the reason to start with an extraction from Wikipedia is twofold. First, Wikipedia is very structured. So it has like the info boxes and the titles and the categories and stuff. So this is actually very helpful. And second, Wikipedia has a certain authority. Yeah. So if you have a dispute with somebody and then you say, I read it on Wikipedia, then you win the dispute, yeah, because you have the authority of Wikipedia. And this is the authority that we wanted as well for our knowledge base. So we first extracted like really from the info boxes and from the categories, but then Wikipedia got actually Wikipedia is very good at the categories and info boxes, but is very bad at the higher taxonomy. Yeah? So if you go up in the categories of Wikipedia, you see like the American singers, super category singer, super categories people by employment or by occupation. That still works. But then you have like occupation, so meaning Elvis would be an occupation, and this doesn't really work. So the Wikipedia is great for the facts, but bad for the taxonomy, which is why we pulled in the taxonomy from another place. And since the rise of Wikidata, we've done the same with Wikidata. So we ingest actually Wikidata, the facts, but the taxonomy of Wikidata is nearly as messed up as the taxonomy in Wikipedia. Yeah? So, for example, Paris, the city, has 60 superclasses, which is already pretty messy. And of these 60, one is mathematical object. Why is that? Because Paris is a geographical entity. Every geographical entity is a geospatial entity. Every geospatial entity is a spatial entity, and every spatial entity is a mathematical object. And so every single link is correct, but the overall path is not. And so we know this problem. Yeah, we have solved it for Wikipedia. We can solve it for Wikidata as well. So we ingest the facts from Wikidata, and we put on top a taxonomy that is from schema.org. And this is how we actually clean this up. And we add constraints, and we like eliminate facts that do not conform to these constraints. And this gives this kind of structure where we have like at the bottom the facts, at the top we have a taxonomy that is relatively clean and allows for reasoning even on this taxonomy. So this is why we call Yago a reasonable knowledge base, because you can actually run an old reasoner and or shackle constraint satisfaction verifier on top of the data, and it will actually work. And this joint work with a large number of people, among whom also May Wish, who actually is chairing this session, or this seminar series. So this gives rise to Yago, yet another great ontology. It's a large knowledge base where we basically pull in all the data from Wikidata, clean it up, remove inconsistent data, and we are left with 50 million entities, 150 million facts, legible entity names, legible taxonomy, and legible schema, and well, some applications in other projects. Good. So what do we do with this? How do we actually complete the knowledge base? Because even our knowledge base is incomplete, and we have a survey article about this. Like, how can we deal with the fact that some data is just not there? How can we fill this up. And I want to talk about one particular approach here, or where we can do two. Yeah, two approaches here. One is filling up facts that are missing. So here, for example, Priscilla Presley, in younger times, was married to Elvis Presley, also in younger times, and she is the mother of Lisa. Yeah? And so then we would like to deduce that if she's married to him and she is the mother of Lisa, then Elvis is probably the father of Lisa. Yeah? I mean, not 100% sure, but like, this is interesting. So we would be interested in finding such rules that you see at the bottom here. Finding such rules automatically. If X is married to Y and X has child Z, then most likely Y has child Z. And this faces two issues. The first one is that you need counterexamples. Yeah? As always in machine learning, if you don't have counterexamples, you risk like learning any arbitrary stuff. And so this will happen here as well. My favorite example is Woody Allen. And Woody Allen was married to his stepdaughter, which is a very weird arrangement. Yeah? And so if you find 5 other people who are married to their stepdaughter, then you will find no counter evidence in the knowledge base for this. And this is because knowledge bases only have like positive facts. They do not store that somebody is not married to somebody. And this is the big problem. These things, you have like 5 positive examples, no counter example, and you will find people are married to their stepdaughter. Now, you can of course say, well, the fact is not there that he's married to his stepdaughter, so then you can assume that he's not married also to Lisa because it's not written there. But by the same token, you should then assume that he is not the father of Lisa because this link is missing. Yeah? So you cannot take facts that are not there as counterexamples because then you shoot yourself in the foot. So here is our solution to this issue. So we make the assumption that if you have some objects, at least one object for a given relation and a given subject, then all the other objects are wrong. So if Priscilla has child Lisa, in the knowledge base, we assume she has no other children. Whereas if Lisa doesn't have any children in the knowledge base, she might potentially have others. And the justification for this is to think that if somebody took the pain to add Lisa as a child to Priscilla, then that person would for sure have taken also the pain to add all other children. Therefore, we conclude that she just has one child, which is in this case even wrong. She had 2 children, but this is the assumption. You can show that if the relation has few objects per subject, like functional relations mainly, but also like relations with a small functionality, then this actually holds true. Yeah, and then we build a rule mining system on top of this assumption. Yeah, any association rule mining under incomplete evidence. And this, program like quite some time ago is still among the state of the art and continuously updated and can find rules. The precision is not good of these rules. The recall is. Yeah, my favorite rule, I don't have it here. Yeah. My favorite rule is that if you are a pope, then you died in Rome, which is a very beautiful rule because it talks about one specific profession and one specific city, and we can mine rules down to this level of granularity. Good. A second way in which knowledge bases can be incomplete is not in terms of missing facts, but in terms of missing entities. So, assume I'm a French researcher and I build a knowledge base of all important cities in the world. Paris, Lille, Marseille, Lyon, New York, Bordeaux. Is any important city in the world missing? Yeah? And I thought it was impossible to actually find that cities are missing until I met my colleague. And the colleague told me it is possible that to figure out that cities are missing, even if you don't have access to external data. And this works as follows. You take each city with its number of inhabitants. So Paris, for example, is like 8 million or something. Right? I think the Paris area is like 13 million. So you take the 13 million, you take the first digit, which is a 1, and you put it into the histogram. And New York is 8 million. And you take the 8, you put it here. And then Bordeaux, I don't know, maybe like 300,000, and you take the 3, you put it here. Yeah, no matter the scale, you just put the numbers there. And you might think there's no reason actually to have these numbers like in any way differently distributed. They should be uniformly distributed because there's a random chance to have a first number 1 and the first number 7. Yeah, there's no reason to have one or the other. And that's not true. There is a law that says that the distribution has to follow this equation. So it will go down. So the 1 is more frequent than the other numbers. And that's a very surprising law. It's called Benford's law. And it is grounded in the fact that cities grow exponentially. And whenever something grows exponentially, it has a higher probability actually of passing through the number 1 than through the other numbers. And that's a very counterintuitive intuition. And but it's true. And if you plot this histogram and you plot the curve, then you can see like you get a lower bound of the numbers of cities that must be missing. And this is how you can actually find out a lower bound of how many cities still must be added. Good. There's another way of incompleteness, which can be filled from other knowledge bases. So consider this setting. So on the left-hand side, we have the knowledge base number 1 that says that Elvis is married to Priscilla. And on the right-hand side, we have a different knowledge base that uses Elvis as well, but say with a different identifier, here, like with a different picture. And like he plays guitar. And now we're going to ask, who is the spouse of the guitar player? And then you don't get an answer, right? Because left knowledge base knows the spouse, but right knowledge base knows he plays guitar. Yeah? So there's no way to actually get the answer unless you somehow map these two entities. And you want to map not just entities, so Elvis and Elvis, but also relations, that is like born in and birth year, which are two relations that are semantically equivalent. So how can we do this? Especially how can we do this without training data? So most existing approaches presume, I mean, what they do is they take the mapping between Yago and DBpedia, which exists, yeah, which is anyway like derived from Wikidata or from Wikipedia, which exists. They remove some links and then they guess the missing links, yeah, which is nice, but it's not realistic because in the real world you might have one knowledge base in one company and another one another company, and nobody will spend like man hours to annotate these things manually and to say like annotate like thousands of entities. Yeah, so you don't have training data in real life. So here's our idea. You start by matching the literals because these are equivalent like by definition, and you give a small degree of equivalence to all relations born and birth year. And then you match two entities if they share relations, like to a small degree, and objects. So Elvis and Elvis get matched to a small degree. And then you say if they have many common subjects and objects, like Elvis and the year and Elvis and the year, then you also align them with a small weight. And then you iterate this. So now the relation alignment is a bit stronger. And so then you will make the entity alignment a bit stronger, and then you will make the relational alignment stronger, and you iterate this thing. Yeah? And it turns out that this process actually converges. I mean, we actually show, we model this in a fuzzy logic way, and then we show that these equations actually converge. And this is why the system is called FLORA, fuzzy logic, object and relational alignment. And it works without training data. It relies on fuzzy logic, so it is explainable. You can actually get the formulas that tell you why two things must be equivalent. It comes with a proof of convergence, and it can work with dangling entities. So even if there is not 100% match, you can still make this system work, and it outperforms the state-of-the-art. So this is our contribution in this field. Good. Yeah, maybe one small geeky thing that I can sneak in here. Once you have the knowledge base, how can you query it? When was Elvis Presley born? You ask the language model, and then how does the language model ask the knowledge base? And the standard way of doing this is to load the knowledge base into triple store, and then comes the query, and then you get the answer from the triple store. Now, assume that the loading is slow. Yeah, to load Wikidata, for example, takes an entire day. And suppose I just have a single query. Yeah, I just want to know when was the guy born. And do I really have to load like the entire knowledge base, figure this out, and then delete the knowledge base in the triple store? That's not so smart. So this might happen, for example, if you want to know whether the knowledge base contains what you're interested in, or you want to debug the knowledge base. Yeah, loading it each time is like huge overhead. And here is a kind of crazy idea: is you could just grab for it. If the knowledge base comes, And you just want to know when Elvis was born. Knowledge base comes in types of like RDF files, Turtle or TSV files or NT files. Just grab. That's slow, but you do get the answer and you don't need to load the knowledge base. And our question was, can you actually translate any query into grep? And the answer is yes. So if you want to ask something more complex, like who were the people whom Elvis influenced transitively, here it is in Sparkle, select A, such as Elvis, influence plus A. Yeah. Then we translate this to a relational algebra tree. I mean, this is standard. Yeah, we don't do this. Then, I mean, it's not our method. Yeah, so we just use standard methods. And then we optimize it. And then we translate every single operator to some bash commands. Yeah, this is how it looks in the end. It's like a pretty messy thing. Now you see the while, and you see lots of sort and cut and move and temporary files and sorting and and joining and stuff. Yeah, so it is a painful to read, but it is for machines to read. And the interesting thing is this little smiley here, which is process substitution. What happens is that Linux or the operating system will start this thing in parallel to the command that consumes it. So the command that consumes it will start consuming, and the contributing processes will start producing, and this will all run in parallel through these things. Yeah, and so I can't resist sharing a review by a VLDB reviewer. Yeah. Unix shell commands to run queries is not very innovative. Yeah, the entire database community exists to overcome the shortcomings of this approach. Of course, was angry because we were actually putting in question his entire raison d'être as a database researcher, and I can understand why he was so angry, because we just outperform the databases. Of course, he doesn't like it. Yeah, so outperform in terms of loading time plus query time. So don't get this wrong. So if you have like lots of queries, it's always faster to load the knowledge base and to index it and to launch the query. But if you have just a single query, then you have to compare loading time plus query time. And that's the only like application scenario where like this approach shines. Yeah. So you see that this system with the bash doesn't time out, doesn't run out of memory. And that's not because we are so brilliant. It's because like bash has been optimized for 4 decades to be extremely efficient on parallelizing, on sorting, and on joining. And so these processes are optimized crazily. And of course, then it works. It's not just because our approach. The nice thing about this is that you don't actually need to download anything. You can go to this web interface, you enter your query here, you click convert to bash script, you get the bash script. Like you don't need to upload any data because the query is actually independent of the data. So you just need you just convert this, and then you get this bash script, and then you copy paste this into a terminal. You trust us a lot, and you press enter, and then this thing will run through, and it will eventually compute your answer, even though it will be slow, but it will actually do it. Good. This brings us close to the end. I still need to answer the question I launched at the beginning of the talk: is Elvis alive or not? And to answer this question, we're going to look into some artificial scenario here, which is all Elvis fans say that Elvis is alive. Among these fans, the author Gail Brewer-Gorjo is this lady here, always speaks the truth. Why? Because she has published a book, Is Elvis Alive? Yeah, and she has absolutely no commercial interest in this legend being spread. Yeah, so we completely trust her. Can we reason on this? It would look like this. For all X, if you're a fan of Elvis, then you say Elvis is alive. This lady is a fan of Elvis, and she always speaks the truth. For all phi, if this lady says phi, then phi is true. So this is the reason we want to do. It's just that it doesn't work in first order logic. Yeah, so you cannot nest formulas inside predicates, and in particular, you cannot like quantify over statements. Yeah, for all phi implies phi. This just doesn't work. This was true, and now it's no longer true, because we have a mechanism called Kiana, quantifying over assertions and agents, that allows you to quantify over agents, reason on formulas in context, quantify over assertions, and assert the truth of a context. And so then our mechanism allows translating this into first order logic, and then you can put this thing into first order logic, into a first order logic reasoner, and the reasoner will actually reason on this in first order logic, and will come up with the answer. And this is the only case in which I can actually prove that Elvis is alive. But in this case, I can actually prove that Elvis is alive. And with this happy conclusion, I would like to thank you for your attention.
Thank you, Fabian, for your presentation. And now we have some time for questions.